Okay, I promised that I would finish making a video that goes over the basics of this polar lesson in case somebody was lacking in their pre-calc skills. So I actually kind of explained already how a point can have a polar representation and how there's an infinite number of representations for that point. I also explained that the origin is called the pole and the x-axis is called the polar axis. And I showed you how you could do parts A, B, C, and D here. Part A I did making a table. Interesting thing was the table was complete when I finally reached theta equals pi. That's halfway around the circle, but it drew a whole circle for me. Interesting. And then for r equals 4, we saw that the absence of theta means that it can be whatever you want. And then on part C, the absence of an r means that r can be whatever you want. We got a line, you remember. And then on the fourth one, D, we created a spiral. It's called the spiral of Archimedes, and it is a pretty common one to test people on. Okay, so we're kind of on this next one, and because I've done this a lot, and because of some of the cheats at the end of this lesson, if you peek ahead, you'll see that these are actually shapes that are very familiar. So this is a four-petaled rose. A four-petaled rose. How do I know that? I have it memorized. Okay? And a four-petaled rose with specifically rose petal length 1. Okay? So it's going to be a very small rose, and it looks like this. I also know some other things about it. I know that this rose has its petals on two of them on the x-axis and two of them on the y-axis like this. In other words, it's standing upright like a cross or a plus sign. Okay? Sine 2 theta, which is the problem just beneath it, is also a four-petaled rose. And that one looks more like this. It's actually rotated 45 degrees to the clockwise direction, or counterclockwise, but there's actually a reason for that I can't explain right now, just because of time, but sine and cosine are usually shifted by 90 degrees, and here we have a 2 theta, so that halves our rotational shift. But the point is, most people just have these two memorized, okay, four-petaled rose. Now, if this had been a 4 theta, it would actually have 8 petals for each, you see? And that's how you handle cosine or sine of n theta. If n is an even number, you get twice as many petals as n. Okay? I'll say it one more time. If this was like an 8 theta, there would be 16 petals. You see? The blue one in front represents the radius of the circle that rose fits in. So for example, if you want a bigger rose, you need to give a larger coefficient or larger amplitude. For example, if you put a 5 here, this rose would be much, much larger and would have a petal length of 5. In other words, the rose fits into a circle of radius 5, which is bigger than the graph paper I've even given you. The same thing with the sine version down below there in part G. Okay, now if the n, that's the number next to the theta, if the n happens to be an odd number, let's say 1 or 3, or 5, okay, if it's cos 1 theta or cos 3 theta or cos 5 theta, then you actually get that many petals. So, for example, cos 3 theta would give you a 3-petaled rose. Cos 5 theta would give you a 5-petaled rose. So when this number is odd, you get that same number of petals. When it is even, you get twice as many petals. So that's all very interesting. It's not that important. What's important for this year is to understand how these points plot and how to use your calculator to plot them. Also, how to make a table if you really have to, which I did back on part A. Okay, some of these things you can just understand just by common sense too. 2 sine theta, that's this one that I haven't done yet right here. 2 sine theta, this problem should be very similar to the problem 3 cos theta. After all, the only difference is the numbers involved. So, and the fact that we have a sine instead of a cosine. But let's take a look at maybe what it might mean. So remember back here on part A, this was a circle, and it was a radius 3/2, and the center was at 3/2. Basically, the diameter was 3, right? and it was actually running right through the pole. So it was not centered around the pole the way this part B was. Okay, this one was centered on the pole, but part A was touching the pole, and it was resting on the x-axis, and its diameter was 3. So just by common sense alone, you can just probably guess that this would then be a circle with diameter 2, right? And it would be resting on the y-axis, so something like this maybe. Now if you're not convinced, you can do what we did earlier. You can take this and multiply both sides by r, like this. And this becomes x squared plus y squared equals 4y. And you can even complete the square. Adding a magic 4 here to complete the square, we get x squared plus y minus 2 squared equals 4. This is a circle with radius 2, whose center is at 0, 2. I drew this wrong. Oh, I don't know why I made this a 4, sorry. This was a 2y. I should have subtracted it over and made a 2y on the left, right here. Completing the square, I should not have added a 4, I should have added a 1. So this is a 1, this is a 1, right here. Minus 1. Glad I caught my error there. Yeah, so this matches my picture. It is a circle with center 0, 1, and a radius 1. That fits perfectly with what I have drawn. Okay, I already did part G. I said it was a rose. Let's go to part H. 3 sec theta. So on this problem, I don't think I would make a table. I would probably just rewrite secant for what it means. It means 1 over cosine. And if I kind of cross multiply this equation, in other words, multiply both sides by cosine, I can see that without any trig or any real calculus or anything, that this is just simply x equals 3 is all it is. In other words, it's just a vertical line. So notice how similar all these equations look, but how different their graphs actually look in the end. That's why a lot of people will take the time to memorize the equations and graphs at the end of this lesson. So let's take a peek at that real quick. Okay, so if you go to the very end of this lesson, you'll see I gave you a small gallery of polar functions. Circles, roses, the spiral, number of petals on a rose, Limaçon curves, which kind of look like lima beans, some of which have a cusp right at the pole, some of which have a little loop-de-doo in them, some of which seem to try to have a cusp but don't, some which look almost completely ovular. Okay, and they all have fancy names and very similar looking equations. Okay, the lemniscate curves. Lemniscates are characteristic, are classic because you can see the r squared right there, and the other side has the ace. It has a 2 theta. So you might think, well, that's a 4-petaled rose, but it has the r squared there. So those are actually more like propeller type shapes. You don't have to memorize these, but you can refer to this if you need. And I think there are some domain errors on here, particularly with some of these more complicated shapes. So we can look at this after you've tried your homework. Okay, so let's go back now and just finish up some of this basic stuff. So scrolling up, I believe this is page 4 of your document. How do you convert to polar coordinates? Well, one way is if the point is on an axis, you don't need any calculations at all. What it's asking you to do is describe the polar location of this point. So you need to tell me how far it is from the origin, that would be 5, and the angle it's at, which is clearly the 0 degrees, or 0 radians. So interestingly, the polar representation for this point is 5, 0. It is at a radius of 5, and it is at an angle 0. So anytime you have a point on the x-axis, positive x-axis here, the Cartesian and the polar representations look exactly the same. Okay, the next one is at negative 2 to root 3. 2 root 3 is about 3.4. So this is our point, you see. And we would seek to find the r and the theta here. So I'm not drawing this to get the answers. I'm drawing this to make sure my calculator is not lying to me when I find my angle. The r is going to simply be the square root of negative 2 squared plus 2 root 3 squared, which is basically 4 plus 12, which is 16. So square rooting that, you get 4. So the r value is 4. The angle is inverse tan of y over x. And you're going to be adding 180 because the x is negative on this problem. So that's how you always know when you're going to add the 180, when the x is negative. Okay, so the calculator will tell you that this angle is negative 60. But we're going to remember to add 180. After all, how can this point be a negative 60? Clearly this is in quadrant 2. So 120 is actually the correct polar representation. So we have 4 comma 120. I actually skipped part B there. Sorry, let's go back and do that. So 0, negative 8 is clearly down here. And you can tell that the r value is 8 because you're actually 8 units from the origin. And you can tell that the theta is simply 270. I'll go and write my answer in the polar radian form. I'm going to write 3 pi over 2. Okay? All right, and then the last one, root 3, negative 1. It's probably around 60 degrees or 30 degrees or something like that. So let's go ahead and just use formulas for this one. So r is the square root of x squared plus y squared, which is just 4. And then you have square root of that being 2. And then the theta is inverse tan of negative 1 over rad 3, which is really just negative 30 degrees. Now I'm not comfortable adding 180 to this because my x isn't negative, but I'm also not really comfortable answering negative 30. I don't like that angle, so we're just going to add 360 to make it look a little more user-friendly. So the correct polar representation is 2 for the radius, 330 for the angle. I'm just adding the 360 because I don't like writing negative 30, but you can, I guess, if you want. Let's go on and look at some of these others where you convert an equation. Okay, so I would just change this r to the square root of x squared plus y squared, and then square both sides. This shows me that it's x squared plus y squared equals 25. This is a circle of radius 5. Obviously, r equals 5 is also a circle of radius 5. For this one, I would replace this with tan inverse y over x equals 30, and I would tan both sides. So y over x equals tan 30. In other words, y over x is root 3 over 3. Since this isn't really in a recognizable form yet, I'll go ahead and multiply by x on both sides. So this is just a line. This is just a line. Okay, this one was a circle. Next one is negative 3 over sec theta, which really just means negative 3 over cosine theta. And if you multiply by cosine onto the left, you can see that this is just simply x equals negative 3, which is a vertical line. Next one looks kind of tricky. Until I multiply both sides by r, watch this, it's like magic. Multiply by r here, multiply by r here, multiply by r here, and I get basically x squared plus y squared equals 2x plus 2y. And you can even bring everything to one side. So x squared minus 2x plus y squared minus 2y equals 0. And I feel like maybe we can complete the square by adding a 1 here and here. Finish my work over here, and I get x minus 1 squared plus y minus 1 squared. And don't forget you add the 1's to the right as well. I almost forgot that. So this is a circle with a center at 1, 1, and the radius is square root of 2. Square root of 2. Good? The right side says 2, but the radius would be square root of 2. Alright, let's clear that off. And let's go on to this page, converting polar to rectangular. Again, what's going on now is you're converting, but this is r and this is theta. So the easiest thing to do is just use r cos theta and r sine theta to convert. So the x and y are going to be 5 cos pi, 5 sine pi. In other words, negative 5 because cos pi is negative 1, and 0 because sine pi is, well, 0. The other way you could have done this problem is imagine a point that is 5 units from the origin over here at pi. Now, give me the x and y coordinates. clearly that'd be negative 5 and 0. Okay, the next one would just be negative 2 cos pi over 3, negative 2 sine pi over 3. So this is negative 2 times a half, negative 2 times root 3 over 2. So the 2's just kind of cancel out on this problem. So the correct answer is negative 1, comma, negative root 3. Now you might say, how can this point be in quadrant 3? That doesn't make any sense. The angle is 60 degrees. Well, remember, the angle is 60 degrees, but that negative there on the 2 means travel in the opposite direction of pi over 3, 2 spaces. So that actually puts you going backwards, away from the pi over 3 rate, down towards the third quadrant there. That's why we got a double negative on our answer. Okay, the next one you can just kind of sketch it, because pi over 2 is actually a quadrantal angle, so 4 pi over 2 is just literally this top point on the fourth circle. So the coordinates are 0, 4. Or, if you really insist, you can do 4 cos pi over 2, comma, 4 sine pi over 2, which is 4, 0. Okay, the next one's the only one that's kind of tough. So let's go to that one, part D. And just follow this very literally. So it'd be negative 1 times cos pi over 12, comma, negative 1 sine pi over 12. And cos pi over 12 is literally the square root of 1 plus cos pi over 6, all over 2. How do I know that? It's called a half angle identity. Okay? It's also listed right here. I just kind of tried to remind you of it right here. Okay? Let's do the sine now. So the sine is going to be negative square root of this. By the way, these negatives here are from here. Okay. 1 minus root 3 over 2. And this can be kind of cleaned up a bit. So you can basically, I think you can rewrite all this as 2 plus root 3 all over 2 and negative 2 minus root 3 all over 2. I'll let you play around with it. That's what I got. Okay, now let's talk about converting equations from rectangular to polar form. This is our last little bit, okay? All right, so y equals x. So you can write r sine theta equals r cos theta, and you'll notice that the r's actually cancel out. Okay? Now keep in mind then that r equals 0 is actually a solution to this. Because if r is 0, this statement is true. So when you cross it out, make sure you keep track of that. Since you're throwing it in the trash right now, you want to write that down. Okay, when is sine theta equal to cos theta? Well, one way to handle that is to divide both sides by cos theta. In other words, when is tan theta 1? That's another way of thinking about it. So this happens when theta is either pi over 4 or 5 pi over 4. Now it's kind of redundant to include both. Let me show you why. We have 3 answers here. I'll highlight them in green. So my 3 answers are r equals 0, theta equals pi over 4, and theta equals 5 pi over 4. R equals 0 is literally just a tiny circle with radius 0. It's a point at the pole. Theta equals pi over 4 is this line here. And if you allow r to be negative, it includes the whole thing. Okay? But theta equals 5 pi over 4 is this line here. And if you let r be negative, it just maps out the right side there. So basically what I'm saying is you don't need all of these. There's a lot of redundancy here. Just theta equals pi over 4 captures every single point that these others do. So theta equals pi over 4 is a decent answer already. This next one, I want to change this to r cos theta, and it's squared. And then this is r cos theta, and it's not squared. And this is r sine theta. So you basically get r squared cos squared theta plus r cos theta equals 6r sine theta and it's extremely tempting to cross out one of the r's in each term. So you're dividing the equation by r. Is this legal? It is if you write down that r equals 0 is a tossed out solution. This might be redundant, we might not need it, but our equation has been simplified and we did throw out a root. So basically, this answer is a little awkward, but r is 6 sine theta minus cos theta divided by cos squared theta. That's awkward. But it turns out that when theta is pi over 4, we actually get, I'm sorry, not pi over 4, but there is a certain theta where this comes out to 0 anyway. So this does contain the r equals 0 case, so the r equals 0 is kind of redundant. I'd have to think about what angle makes 6 sine theta minus cos theta equals 0. So you have to kind of play around with that maybe. I think I'll figure it out here real quick. I think it's like 9.5 degrees. Okay, but see, that's the polar representation. Notice that the polar representation isn't a very friendly looking equation. Okay, but that's okay. This next one's really easy. This is just simply r squared, the whole bit. So you can write r squared equals 36. For square rooting, we get r equals plus or minus 6. It's kind of redundant to include plus 6 and minus 6, because r equals plus 6 is this sixth ring here, and r equals minus 6 is the sixth ring also. It just kind of plots from the opposite side. So either way, it's the circle radius 6. Typically, we often can toss out the negative root when we get a plus or minus like this. Okay, the last one is r cos theta times r sine theta equals 5. And if we multiply those r's together, we get r squared cos theta sine theta equals 5. And if you divide by cos theta and sine theta simultaneously, we get r squared equals 5 over cos theta sine theta. You can square it if you want, but it's also kind of a tradition to have r squared in the answer. We saw that a moment ago at the very bottom of this document when we looked at the Leibniz case. They had r squared equals a squared sine 2 theta and r squared equals a squared cos 2 theta as the equation. So it's not wrong to have the square there. If you need to type it into your graphing calculator, you need to square root both sides, and you get plus or minus square root of 5 over cos theta sine theta. And you'll have to decide if the minus is actually redundant or not. So you can graph as r1, the positive case, and graph as r2, the negative case. And if they seem to be the exact same graph, then I wouldn't stress about it. Just toss out the negative solution. Tomorrow we'll talk about how to find area within a polar curve. For example, the simple question of what is the area inside a cardioid. That turns out to be a fairly complicated question. So we'll address that tomorrow, but I'm talking about this graph right here. For example, how do you find the area inside it? You can't use pi r squared, right? We're going to use integration. So stay tuned.